1 inch and 1 inch here, 1 here. Everything is here, and then I say if the axis, if my coordinate system is here, xy, give me this formula: a x bar is equal to 0, y bar is equal to 1.5.
Maybe switch.
Hold on, I'm going to give you some options. Y bar, x bar is equal to y bar, c, x bar is equal to 1.5, y bar, 1.5, d, x bar equal to 0, y bar. So this is a good example that I will give you like a bunch of these, like 6, 7 of these examples like that. So obviously you know that you don't have enough time, like you have 2 minutes per question like that. So you don't really have time to create this table. In fact, you could decompose this into shape 1, shape 2, shape 3, 4, and 5 is the green color. You could decompose it into 5 different shapes. 1, 2, 3, 4, and 5. And now you have the formula for area of each one of these and the centroid with respect to here. For example, centroid of this with respect to here is 1.5 x centroid. Y centroid is 0. And you have formula for A1. So A5 is 1 by 1 inch squared. So you have everything to fill out the table. But look, if I give you 5 or 6 questions like that, you don't have time to make that table for every single of these. But you know that this is symmetric. So the centroid is right here. It's perfectly symmetric. So the centroid is right here. The next thing you ask is the coordinate system. Where is my coordinate system? If the coordinate system is here, so the x of centroid is 1.5, y of centroid is 0. So that's the correct answer. Now if I put my coordinate system, if I, instead of here, I show the coordinate system right here. Let's use blue. Back. I will put coordinate system right here, x, y. Now I give you exact same question. I'll just change the coordinate system. So what's the correct answer with the x, y at this bottom? Is A. You see that? It's A. So always check where your coordinate system is. In what respect you are measuring, what's the difference? Okay? Now let's go to the moment of inertia. Now so far, we computed integral that involves geometric centers. So in the geometric center, so let's put it here, moment of inertia. area actually, area, moment of inertia. So far we have formula like x bar integral x dA over integral dA. You could see that the power of x is 1. And we use this for the centroid calculation. Now if I have a formula like, if I up the power x through 2, they call this particular integral, engineers call this integral as I moment of inertia. So this is called area moment of inertia. Why area moment of inertia? Because here the integration parameter is dA, the integral over area. And why moment? Because you're computing some distance times a weight. You see that? But don't forget that this is power 2. If you have power 1, that integral is still useful, but it's only used to find the centroid calculation. It's not for moment of inertia calculation. Now, just this is enough to finish up this section. This section is nothing except compute this integral over a bunch of shapes. And then the final conclusion is, well, if you know how to compute it, there is no point as an engineer to take this integral every single time. You go to a table, in the appendix, it's called table of moments of inertia. And you just look up the formula you need for that particular shape, like if it's a triangle or circle or rectangle. Then you just, somebody took this integral and just give you the formula and you just use it, right? Now let's do an example. Let's say we have the simplest possible shape, which is a rectangle, and the base, call it B, width, call it A, and put your coordinate system right here, x, y. Now the question is, find the moment of inertia, I. So now another thing, when you choose the axis, you just put as a subscript. So IY will be, this is IY, x squared dA over the area, integral over the area. So this is two-dimensional integral. It's an area integral. Don't forget this. This is the integral over the entire area. So when I say I with respect to this y-axis, that means find the distance of all the element with respect to y, which is obviously x, times the dA. Take the integral times dA. So now I want to give you another opportunity to be able to get a better grade in the midterm. How do you find this integral over this area? This is a calculus 2 problem. How do you evaluate this integral for this shape? And this is a reference coordinate system.
Wouldn't that be turning it into 3D?
No, this is just two-dimensional. So how do you evaluate this integral over this area? Well, the first thing in order to get, the first thing in order to evaluate the integral is to take the element, right? You have to find your dA. So if I take an element like that, and this is infinitesimally thin. So here, x, from here, this x coordinate, and this becomes dx. Because this is infinitesimally thin, right? So dx. That's x, that's dx. So what's dA? All I want is to compute dA, plug into formula, and take the integral. Right? So what's the formula for area of this part? dA is equal to A times dx. That's it. So I got formula for dA. So I just put it right here. So that's going to be integral x squared is already in the formula. This one is coming with the formula, so you just leave it. Times dA. And what's my dA? A dx. And don't forget, A is a constant. A is a constant. So here, what are the bounds for integral? The entire shape. So x is from 0 to b. Right? Now the question is just evaluate that integral. So what should I do? This is a constant, take it out. So put it here. So x squared is x to the third power a times x to the third power over 3, right? From 0 to b. So that's going to be a b cubed over 3. That's the final answer. You see that? Now, if I ask you, okay, this is Iy, find Ix. Again, we have a formula. Ix, that means moment of inertia with respect to the x-axis. This x-axis here. Always look at the coordinate system, it's here or here, whatever it is. So that means if I take an element like that, right, the distance of the element with respect to x-axis, which is y. So you have to evaluate y dA integral over the area.
Y squared.
Huh?
Isn't it y squared?
Is that what?
Isn't it y squared?
Yeah, y squared. Sorry. Y squared. So this here, all I did, I just changed x with y. So you get I x is equal to y squared dA. So in fact, it's the distance squared times dA with respect to corresponding axis. So if I do Ix, that's going to be y squared. It's just flipped. So before you compute this integral, what should be the final answer?
BA cubed over 3.
Yeah. It should be y. Because look, you just switch A and B. Because in the other direction, you have a rectangle. So it's you just switch the A and B in the formula. B, A, so the final answer should be B. So instead of A, you say B, and then B, you say A cubed over 30. Now let's do the integral, the actual integral. See if we can get this number. So this is going to be, for this element, dA is equal to this length, which is B times this length, from here to here. So if this is Y, this infinitesimal length is dy. So just let's plug it there. So you get integral y squared, it comes to the formula, times dA. dA is b dy. From, now integration is over y. So it's from 0 to, is 0 to A. So you get b, take the b out, right here. So you get b times y over 3 from 0 to A, so you get B Q over 3. Isn't it the same number right here? The same formula, the same thing. But we use the rule of symmetry to get the rules of symmetry, as I said, they are very powerful rules in physics. They solve big, very advanced problems. But the simple application here, it can accelerate your computation. You can just avoid this integral. I'll just say, I just flip A and B and get formula in the y direction. Right? Now let's go solve this example, the triangle. Before we go to triangle, let's find the moment of inertia. Let's say we have the same geometry, B and A, but I want to find the moment of inertia with respect to the coordinate system going through the centroid. So I know the centroid is here, right? So if the coordinate system xy is passing through the centroid, now give the formula. And it turns out this is a very important integral. So finding the moment of inertia with respect to centroid is the thing that we need in the second part of the course, mechanics of material. You want to find the moment of inertia with respect to the centroid in order to put in the beam calculation formula. So in the beam theory, you draw a formula that there is a moment of inertia, area moment of inertia, but that one requires you to find the centroid and plug it into the formula. So you should be able to find the moment of inertia with respect to centroid. Now let's compute that integral when my x is at the center. So y is integral x squared dA. Right? Again, let's take the elements like that. So that's your dA. So this is going to be x, and this is going to be dx. So dA is equal to A times dx. So far, same. It looks like everything is the same here. Looks everything. See this black one? This black one, the area was A times dx. But if I plug it here, let's plug it in the formula. So I have integral x squared times dA, which is A dx. But from where to where? Now that's the point. From where to where? X from negative b over 2 to b over 2. So you get, take the a out, it's constant. So you get a times, that's going to be cube over 3 from negative b over 2 to positive b over 2. So that's going to be a times, put b here. So you get b third power, and that's going to be a times 3, 24, plus b cube 24. You see? And then you get a times b cube over 12. What we got first was a times b cube over 3. But this was with respect to this corner here. It wasn't with respect to centroid. With respect to centroid, that number becomes 12. Now go to the appendix. Go to the end of the book. In particular, if I find the appendix, I'll find it. Thank you. So you go to Alright, if you go to page 814, in particular 815, if you go to page 815 on the top, you see that you have a rectangle, and then you have Ix is 112b cubed, and Iy is 112hv cubed. That formula is exactly the same here, everybody. As a matter of fact, somebody does this formula and verify the formula is right, and they tabulate their finding. So as an engineer, you don't need to evaluate the integral every single time. You just go to the appendix, or you can just go to Wikipedia. You can Google it. Say table of area moment of inertia, and it just brings you a lot of different shapes, like triangle, rectangles, circles, trapezoidal, a lot of different shapes. That all you get is this formula for Ix and Iy. You don't need to do integral. All you need, you get the formula, and then you make sure the centroid, the formula is computed with respect to centroid. Sometimes they evaluate the formula with respect to some point that is not the centroid. And then all you need to do is to transfer it to the centroid. That's the subject of a theorem we will discuss later. This, as a matter of fact, this is the last thing we will discuss in the class. It's called parallel axis theorem. Parallel axis theorem. So this theorem transfers moment of inertia from a point that is not centroid to a point that is centroid, and vice versa. You can find the relation. It's like a transformation formula, right? And that should be the last thing we discuss in the class. Then when we finish the class, then we come back and solve a lot of examples, and we do comprehensive quizzes and study, make sure that we get ready for the final exam. Yeah?
Figured it out, never mind. I was confused as to why you said b over 24, but it's because you cubed the 2.
Yeah.
8 times 3.
Yes, you cube the 2 at the bottom, so 2 to the third power is 8 times 4.
But where did the minus go? Where did the negative go?
This is odd. You see, x to the third power is not squared. So negative to the third power is still negative. Times the negative integration.
Oh yeah, it's minus. Okay.
It's negative times negative is positive. It's a good exercise when you go home to verify these things, double check. And you may, I give you an option on this optional homework. You don't need to turn it. Find I, Y, Ix. So this is Iy. Find Ix. What do you expect for Ix to be before you solve it?
B8Q.
Exactly. B8Q over 12. Because the same rectangle, just use A and B. Now you go home and do this integral again and see if you can get the same result or not, just for verification. Huh? It's not big, it's just this shape.